Hello everyone and welcome back to the course. Today we push the boundaries of calculus as we delve into the fascinating realm of how functions behave as we approach to infinity. First of all, let's have into account that the symbol for infinity represents an extraordinary big quantity, and with that into account, we can have a better understanding of the algebra of infinity. For example, if we have infinity plus minus a number, no matter how big or small this number is, it will be equal to infinity. Infinity times any number will be infinity if the number is positive, or negative infinity if the number is negative. And any number, n divided by infinity, will be equal to 0. Now, the symbol for infinity can come as handy when it comes to limits, because every time that we're trying to analyze the limit when x goes to infinity or minus infinity of any function, what we're trying to analyze is actually if the function has any horizontal asymptote. For example, if we take into account the function 1 over x and we analyze the limit when x goes to infinity or minus infinity of such a function, either by looking at the table or by looking at the graph, we notice that such limits go to 0. So we can say that 0 represents a horizontal asymptote for such a function. Another example in which we can use the limits when x goes to infinity or minus infinity for noticing if the function possesses any horizontal asymptotes is the function f of x equal arctangent of x. If we do the limit when x goes to infinity of such a function, we get pi over 2. But if we go to minus infinity, we get minus pi over 2. So we can say that those two values represent horizontal asymptotes for the function. Finally, if we take into account the function f of x equal e to the x, then we can notice that if we analyze the limit when x goes to infinity of such a function, the values of e to the x increase extremely fast. Actually, it doesn't have any bounds. Therefore, it doesn't have a horizontal asymptote when x goes to infinity. Nevertheless, when we go to minus infinity, we notice that we get closer and closer to 0. So 0 represents a horizontal asymptote for the function e to the x. Now, let us consider the following limits. The limit when x goes to infinity of ln of x, the limit when x goes to infinity of x to the 5, and the limit when x goes to infinity of e to the x. Now, all of those limits go to infinity, but what would happen if we do some other combinations of limits, like this ones? Now, if we try to solve all of those limits, we get really weird answers like infinity minus infinity and infinity over infinity. And those answers actually don't tell us much. Now, let us consider the following table, which consists of the functions ln of x, x cubed, and e to the x. Now, we are going to approach bigger and bigger values of x to see which is the behavior of all of these functions as we approach to infinity. And as we can notice, if we increase the values of x, all of these functions increase as well. Nevertheless, e to the x increases faster than x cubed, and this one increases faster than ln of x. So we can assure that the infinity of e to the x is way bigger than the infinity of x cubed, and this one is way bigger than the infinity of ln of x. Actually, we just put this particular case of x cubed, but this actually works for any polynomial. Therefore, we can say that the infinity of e to the x dominates the infinity of any polynomial, and the infinity of any polynomial dominates the infinity of any logarithmic function. Now, let us consider the limit when x goes to infinity of ln of x divided by x cubed. Now, we know that the infinity of any polynomial is bigger than the infinity of any logarithmic function. Therefore, this limit goes to 0. Finally, if we have the limit when x goes to infinity of e to the x divided by any polynomial, this limit will go to infinity because e to the x at infinity dominates the polynomials. For finishing the analysis of limits that go to infinity, we're going to consider the following case in which the involved functions are of the same type. For example, we're going to work with polynomials in this case, but actually this works for any particular function. It doesn't matter if it's a logarithmic one, a radical one, or an exponential one. Let us consider the limit when x goes to infinity of x cubed plus x squared divided by x squared plus x. We can divide by x squared both the numerator and the denominator, and if we do the naive substitution, we get infinity over a number, which by the algebra of infinities, we get infinity. If we do the opposite, that is, the limit when x goes to infinity of x squared plus x divided by x cubed plus x squared, and we divide by x squared both the numerator and the denominator, and we do the naive substitution, we get a number divided by infinity. And by the algebra of infinities, we get 0. Finally, let us analyze what happens when we have two polynomials and they have the same degree. For example, the limit when x goes to infinity of 2x squared plus 1 divided by 3x squared plus x. If we divide by x squared and we do the naive substitution, we can notice that we get 2 over 3. Therefore, we can say that if we have two polynomials in a quotient and the highest degree appears in the numerator instead of the denominator, then the limit when x goes to infinity of such function goes to infinity. Otherwise, it goes to 0. Nevertheless, let us say that we have the quotient of two polynomials with the same degree. Therefore, the limit when x goes to infinity of such a function goes to the coefficient of the monomials with highest degree. I challenge you to solve the following limits. By doing so, you will be expanding your knowledge to infinity and beyond.